In this video, we're going to look at several questions on thermodynamics and mostly involving gas laws. So for the first one, it says using the kinetic theory of gas, which of the following best represents the root mean square speed of 58 grams of monatomic ideal gas at a pressure of 3 atm in an enclosed container of volume 6 liters. So to calculate the root mean square speed, I suppose we need to use the expression for kinetic energy, and as it is an ideal gas, this means that the kinetic energy is just equal to the internal energy, and I suppose using that equilibrium, we can calculate the velocity. So let's see, the expression for internal energy of a monatomic ideal gas will be 3/2 and then PV, and that is equal to a half mv squared for its kinetic energy. So in this case, what we can do is rearrange for V first of all. So V will be equal to the square root of, we can cancel out the 1/2, and what's left will be 3 PV over M. And then we can simply plug in the numbers. Yeah. So the pressure is given, right? Yeah. So the pressure is given as so this pressure is 3, and then it's 3 atm, so 3 times 10 to the power of 5, and then you time it by the volume. If you convert liters to cubic meters, that would be 6, and then times E minus 3, and I think I need to add brackets, so minus 3, and then over the mass, which is 58 grams, so minus 3 again, and that is equal to invalid number. There might, oh yeah, I think it's just minus 3, or else it's assuming that it's multiplied by minus 3. Most likely. Let me try. Yeah, okay, so that will be 305, and then, so that's 305 meters per second. So that will be most likely D. And then for the next question, it says in a mixture of hydrogen, oxygen, and nitrogen gases at room temperature, the molecules having the greatest average speed are those of these choices. So at room temperature, so this means that they are given the same amount of internal energy. And essentially from the last question, it's the internal energy is equal to the kinetic energy. So what determines their speed is basically their mass. And in this case, hydrogen has the least mass, so it will have the greatest average speed. Yeah, has the least atomic mass. And for the next question, it says 3 identical samples of a monoatomic ideal gas are taken from a temperature T to a temperature of 2T. So twice the temperature, and then sample A undergoes an adiabatic process, sample B undergoes an isobaric process, and sample C undergoes an isochloric process. Which of the following correctly ranks the heat added to samples during these 3 processes? Heat added, so I suppose for this question, we need to draw simple graphs for it, and the heat added cannot be determined directly from it. So I suppose we can use the first law of thermodynamics. So U is equal to Q minus W or plus W. I prefer minus W. And so in this case, what we can see is that from T to 2T, so essentially the change in internal energy will be the same for each of these samples. And the only thing that determines the heat will be the work done. So let's see, sample A undergoes an adiabatic process. I'm going to draw graphs for comprehension. So that's PV graph, and then essentially for an adiabatic process, it will be from this point to this point, because from left to right, the temperature will decrease as there's no heat added and then there's work done by the gas. So therefore, it must be a reverse process that increases the temperature. And in this case, the work done will be positive in the sense that it's work done on the gas. So in this case, well, like positive, if we're going to say the work done is positive, then I should change the symbol to plus, like this, and then so that will be, so QC will definitely, so that's QA, yeah, QA will be definitely smaller than the change in internal energy. And then let's see, for sample B, it goes to an isobaric process, so that's a constant pressure, and essentially it will look something like this. It will be a straight line or a horizontal line, and we can see in this case the work done is by the gas, so therefore that will be negative. So this means that QB must be greater than the change in internal energy. And then QC, it says undergoes an isochloric process, so that's just like this. It goes up like this. There's no work done, so therefore QC is just equal to the change in internal energy. Yeah. So if we rank these, that will be B, yeah. And then for the next question, it says when the ideal gas is taken through an isochoric process, done through an isochoric process, so that's just constant volume. Well, we can see it's just the work done is equal to 0, yeah. The work done is equal to 0, and then the rest is incorrect. And then for the next question, it says two identical samples of a monoatomic ideal gas are to undergo reversible processes. Which one of the following choices is a correct statement about heat associated with the processes? Process 1, an isochoric pressure doubling. Process 2, an isobaric volume doubling. Okay, and then so, yeah, okay, identical samples of gas. So there's less heat associated with process 1 than process 2. So in process 1, let's see, it's a constant volume process, and essentially it will look something like this. It's a constant volume process, so it will look something like this from this point to this point. And then for that's process 1, and for process 2 it will look like this. So the volume doubles, yeah. So let's see, there's less heat associated with process 1 than process 2. With process 1 than process 2. So with process 1 there isn't any work done. And then let's write the equation over here. So change in U is equal to Q plus W. Therefore, more heat will be involved in process 2. Because work is done by the gas, and then essentially this means that more heat is added to its system in order to maintain the same change in internal energy. So that is correct. So okay, the first one is actually correct. And then let's see the other choices. So the heat is the same non-zero value for process 1 and process 2. That is incorrect. There is more heat associated with process 1 than process 2. That's just the opposite of the correct answer. And then the heat is 0 for process 1 and process 2. That's incorrect. More information required, and we can actually determine it. So A is correct. And then Let's see, the next question says a gas undergoes the unusual process M to N. In the pressure vs volume gas graph shown, which one of the following choices probably represents a sign of the internal energy change of the gas, delta U, the total energy transferred as a gas as heat to the gas, Q, and the total work done on the gas by the surrounding W for this process. So let's see. What we can determine first of all delta U. So the change in internal energy we can say is that the internal energy is equal to like a certain coefficient that is determined by the whether it's monatomic, diatomic, or any other polyatomic gas. So let's say just K and then times PV. So in this case, if you compare M to N, we can definitely see that the internal energy at M is definitely greater. So therefore, the change in internal energy must be negative. So we are looking at B, C, or E. And for Q, I suppose we can look at the work done first. So the work done in this case, it says in the question total work done on the gas. So in this case, the volume decreases, so therefore it has a positive work done on the gas. And the answer should be E, yeah. So the last question says 1 mole of ideal gas initially at temperature T0 and volume V0 undergoes a reversible isothermal expansion to V1. A reversible isothermal expansion to V1 if the ratio of the specific heats is Cp over Cv, which is equal to gamma, and if R is the gas constant, the work done by the gas is. So the question wants us to derive the work done by the gas in that isothermal expansion. Okay, so let's see. So in order to calculate work done, I suppose in this case we need to use a bit of integration, and to use integration we need to calculate the function of such graph, and then so it's an isothermal expansion. This means that PV is equal to nRT, the ideal gas law, to determine it. So isothermal expansion, so this means that the temperature does not change. The only variables in this equation will be P and V. So if you express P in terms of V, that will be P is equal to 1 over nRT times V. So yeah. And then what you can do is simply integrate this. That will be from V0 to V1, yeah, V0 to V1, and then of this V times dV, and what we'll get is, see, we can factor out the constant, and then what's left will be, oh wait, I got this the other way around. Okay, so that's the other way around. I don't know why I did this. Okay. nRT over V, and then yeah, nRT. So the inside will be natural log of V, and then yeah, natural log of V, and then V from V0 to V1, and then it will give us nRT, and that will be ln of V1 over V0. So from the choices given, there's only RT0 ln this, so I suppose if it's 1 mole, yeah, and then the temperature remains constant at T0, then that will be RT0. So therefore the answer will be E.